Alright, so let's do angular momentum. Double check to make sure that's in the field of vision. And, yeah, it looks fine. Angular momentum. Well, before we talk about angular momentum, let's talk about linear momentum. Linear momentum. Usually written P equals mass times velocity. So linear momentum is mass times velocity. And we not write a bar over the P and the V to indicate their vectors. That'll become significant, especially it would really be significant when we talk about angular momentum. But yes, we have mass times velocity, and Newton's second law states that force is equal to, we're used to hearing it said that it's mass times acceleration, but actually what Newton's second law states is that force is equal to the change in momentum. So we have the bars over them to indicate their vectors, and the dot over the P, or maybe right like this. The dot being Newton's notation, this being Leibniz's notation. Dot. Force equals time rate of change of momentum. If the mass is constant, then the derivative of momentum is derivative of mass times velocity. And if the mass is constant, it comes out of the derivative, and we get the time rate of change of velocity, which is acceleration. So we get mass times acceleration. So if mass is constant, it takes the form force equals mass times acceleration. Sometimes mass isn't constant. Usually it is, but when you're analyzing, for example, a rocket that is losing mass through its exhaust, you really then do need to use Newton's second law in this form, because this analysis here doesn't hold, because you can't just pull mass out. Mass is actually changing with time. You have to do a more complicated analysis that this doesn't apply. But let's see, we have Newton's second law that force is time rate of change of momentum, linear momentum. Gets that out of the way. Now, angular momentum. Let's just, for right now, let's just define angular momentum L as R crossed with P. So, if we have some coordinate system, and we have a particle here moving velocity v. Let's even just go ahead and let's say velocity v, and have a momentum vector in the same direction, mass times velocity, momentum. I want to change colors there or something. Make that a little more. The particle is moving with velocity v. There's also, say it has momentum, it's mass times velocity. So it's going to be in the same direction, might have a different magnitude. That's the P. And it's got some position in some coordinate system. And that's our position R. And we're going to define the angular momentum with respect to some origin as the cross product of the R and the P vector. And first of all, just intuitively what that is it is the product of the lengths of the vectors times the sine of the angle between them, and the vector is oriented in or out of the board depending on a right-hand rule. So R cross P in this case would be R going this way, P is this way. Actually, you'd want to you do the cross product. The R is in this direction, P is over this direction. The right-hand rule, curling your right hand from the R to the P, indicates that the cross product is going to be like, well, it's hard to draw that, but it's pointing straight out of the board. It's pointing this way, and it has magnitude R, P, sine theta, where theta is the angle between the two vectors. Yeah, let's just define angular momentum as that, and I'm going to talk about that a little bit more. But just put one more definition up on the board, and we'll come back to that. Define torque as T equals R cross F. So we take cross products of momentum and force. The cross product of the linear momentum gives us angular momentum. The cross product of force gives us torque. So basically, we have force being exerted this way. If you think about it, exerting a force in this direction causes the whole thing to tend to want to twist angular momentum. The sine term is significant. If say the angle between the two vectors is 0, then the sine is 0. What does that mean? It means the force is just going out in this direction. We have some other, if our force is acting this way, the angle between the R and the F is 0 because they're in the same directions. The sine is 0. Yet there's no twisting going on. You're just pulling it out. You're not doing anything to turn it. That's kind of the intuitive definition. I'm going to talk about that a little more, make sure everyone's clear on these concepts. I'm going to define the cross product mathematically. Let's say, let me say here, given vectors A and B, with Cartesian coordinates, let's call it AX, AY, AZ, and BX, EY, EZ, then the cross product is A cross A. And you can write this in a couple different ways. Easiest way to remember it, if you're comfortable with advanced mathematics, is just the determinant of kind of a weird matrix. Determinant of our unit vectors x, y, z up here, ax, ay, az here, bx, by, bz here. And I'm just going to take the quote-unquote determinant of this thing just by applying just mechanically the determinant rule. And if there's any confusion about what that is, well, now I'm just going to write it out. Let's see, the x term is what we have, ay and bz, and then we have a negative term here, minus az and by. Those are our x components. And then for our y component, we're going to have, looks like an az bx term minus an ax bz term. So our y component and our z component is then going to be ax by components, the x component is formed from the y and z components, and then we have them in one direction. We reverse the order of the components, take the z and the y component, and we flip the sign. And we do the same thing. Y component is formed from the x and z components. The z component is formed from the x and y components. And the significance of all that is that I want to be able to take the derivative of one of these things. So what happens if I take the time derivative of a cross product? Well, I'm going to take the time derivative of all of this thing. Derivatives of additions, derivation commutes with addition, and it also commutes with subtraction. So I'm going to end up taking the derivative of each of these 6 terms individually. And what am I going to get? I'm just going to apply the product rule. I'm going to do this here. I'm going to apply the product rule here. I'm going to get what? AY derivative of BZ plus derivative of AY and BZ. That's applying derivative here. And then I'm going to subtract this one. It's going to be AZ dy. Hopefully. And I'm going to take some time to go through all this. I'm going to take some time to go through. We got the derivative of AZ, dg, dy, and this whole thing is the x component here. And let's see, I don't want to wipe out the. I'm kind of running out of board space here. Let's just say, I might write it out for the students, but for you guys, I'm just going to say something similar for the y and z terms. Because what I really want to do now is collect my terms, and I want to pull, what do I got here? I want to show this is in fact equal to the, I know what the answer is, so we just write it up here. Derivative of A cross B. Let's write that a little differently. B plus A cross derivative B. And might want to either go through all this on the board or sign it as a homework problem just as an exercise in vector manipulation. I'm not sure. I haven't looked at the AP curriculum. I'm guessing that vectors, I just suspect vectors are probably in it. I didn't take AP physics. I took it in college. Anyway, and we can look here. We can take the derivative of the A is A here, AX plus AY plus AZ is the Cartesian coordinates. The derivative of A is going to be let's write this out here. Let's see how this goes. Right. Yeah. And when you plug that expression of the derivative into here, and you collect all your terms together, you get this thing, which establishes this identity here. The time derivative of A cross B is in fact, basically, what you're just showing is that the product rule works for cross products, just like it does for theorem products. So cross product rule. And now what we want to do is we want to take cross products over here. What we want to do, we want to, we already have cross products, we want to take derivatives over here. So the time derivative of angular momentum is going to be the time derivative of r plus r crossed into the time derivative of t. Now, we know that the time derivative of r is just, r is the position of the particle, so this is the velocity of the particle. but the momentum is just mass times velocity. Let's leave this alone for right now. And just look at this first term. We're crossing a vector times a scalar multiple of itself. Well, I've already seen that if you're crossing things along the same line, the sign is 0. That's certainly true here. The angle is 0 because it's the vectors in the same direction, which is a scalar multiple of the first one. So the sign is 0. So this whole term here goes to 0. And that leaves us with r cross time derivative of momentum. But Newton's second law already tells us that the time derivative of momentum is, in fact, force. So this is r cross f, and that's torque. So what this shows us is that the time derivative of angular momentum is torque. So we have an exactly analogous relationship between linear momentum and angular momentum. Linear momentum is mass times velocity, and its time rate of change is force. Take cross product of everything, we get angular momentum and torque. Time rate of change of angular momentum is torque. How does all of this help us? Well, it actually helps quite a bit more, first of all, analyzing any kind of rotational problem where things are rotating. And by judicious choice of our coordinate system in particular, notice that the choice of coordinates is kind of arbitrary here. We get different answers depending on where we set our origin. A lot of times you can set your origin so the torque just becomes 0. You set your origin at the rotational center of your system, and then your angular momentum is conserved. You can also use this to analyze something like a rotational spring. We have something like spinning, rotating around, and there's a spring that's bringing it back to some rotational center. A common example that's used a lot is the way figure skaters pull their arms in to speed up their rotation. Let me just put that up over here. Let me go for time. About done. One more thing. Moment of inertia. Yeah. Moment of inertia. Let's see here. This is all for a point mass. If we do this for a continuous distribution of masses, we would integrate over our entire mass. And in particular, we want angular momentum is r cross p, which is mv. And now I'm going to take a particular choice of r. I'm going to choose a center, a rotational center. So I'm going to have a rotational axis, and I am rotating around that axis some angular momentum, gamma. Sorry, that's not gamma, that's omega. So omega is in radians per second, say. And if we multiply it by radius, I might be missing a pi or something here, but r times, you think of something rotating. The radius times omega is going to be meters per second. So this is our velocity of some point here, out here. Let me just think about that for a second. If omega is radians per second, yeah, r omega is meters per second. Okay. This is my velocity, v. I've written as a scalar now because we've picked a particular axis. It's not a vector in this formulation now. V, and let's see here. So let's write this out as r, and because we're rotating around, our velocity R M R omega r squared mass times angular velocity. And now, if this is a solid body, I'm going to replace the mass with the mass density and integrate over the whole thing. So I'm going to factor out my omega, which doesn't depend on the geometry. I get an integral of r squared, I'll just call it rho of r dr. And this quantity here is the moment of inertia. I. And that means that L is omega I. The significance of I is that it depends solely on the geometry of the object, and it is not dependent on the rate of rotation, omega. Also, it's directly related to angular momentum. I'm dropping the vectors here because I've picked a particular axis, everything's spinning around, so now everything's relative to a particular axis, so I'm just doing everything as scalars. And if there's no torque, we've already shown here that this is conserved, so L is constant, and that's how the figure skater does her trick. What she's doing is she's pulling her arms in, she is decreasing her moment of inertia because she's pulling the mass in, the radii goes down, that means the moment of inertia goes down. In order for L to stay the same, if I goes down, omega has to go up, so the rotational speed increases. It's another important technique that's used for analyzing a lot of rotational problems when you're dealing with rigid bodies. You can calculate the moment of inertia of the body around a particular axis that it's revolving around, and then a lot of your calculations simplify from there. And I think that's plenty on angular momentum.